So I just spent the better part of a day turning a small piece of aluminum into a smaller piece of aluminum, but why? Like, what was the goal behind this? Well, the spectrometer can be used to measure just about anything, gas, liquid, or transparent or translucent solid. But I want to start with liquids, which means I need something called a cuvette, and that's what I have right here. This is essentially a square test tube, specifically meant for use with spectrometers. It has to be square so that way when the light strikes it, you don't get an angle of refraction and the light changing directions in and out. But I didn't have a place to put the cuvette in the sample chamber. Mike hooked me up with this very interesting thing here that sits on the proper kinematic mounts in the sample chamber. And I don't particularly know what this would be used for, but I do know that it can't hold a cuvette. So I pulled this little iris piece out, took a bunch of measurements, and we machined up this little square that slides perfectly into this and has a 14 millimeter deep square pocket for me to put a cuvette into. Now, I also put a little slot in front of the cuvette pocket for a neutral density filter to slot into. Now, the neutral density filters are 1 inch round and actually will fit into the filter wheel up by the sources. So why wouldn't I want to put a neutral density filter up there? Well, I'm not sure that those filters can handle the amount of energy and heat being produced and focused down onto them. So if we put it all the way down here, we can have a filter up in the filter wheel that's like steel mesh or something, cutting down the total amount of energy. And by the time it gets down to the neutral density filter down here, it's not going to hurt or damage anything. Also makes it pretty easy for me to change filters pretty rapidly by just getting into the sample chamber. Now, that problem of there being way too much energy coming out of the sources is one that we need to address, because right now, if I don't have a piece of paper to block the light, it is way too powerful and we get no usable signal out of that. Ultimately, this is a Fourier transform infrared spectrometer. But it's so well built and so well designed that they discovered that it was actually pretty capable in the near infrared and even into the visible, which is the setup that I have going on right now. I have the quartz beam splitter, the visible near infrared detector, and for a source, we're using essentially a car headlight bulb. On the unfortunate side of that, it puts out a nice white light, but it also puts out a phenomenal amount of power. So that energy is way too high, and Bomem themselves realized this, and they started making modifications to the system to reduce the amount of voltage going to that 12-volt bulb. And we actually saw one of these modifications early on when we were trying to revitalize this power supply down here. They did that in the form of a diode. They had specific diodes that they used that had about a 1-volt drop on it. And I didn't realize it at the time because that one was all corroded and rusty and bad. That when I replaced it, I put in one that has about a 0.6-volt drop. So that diode is specifically there to reduce the amount of voltage making its way to that light bulb. So we actually ended up making it brighter, and we need to make it dimmer. So I need to machine up a little PCB that has, I'm gonna put, I think, 4 diodes on it. That should give us about a 2-volt drop and reducing the total amount of power coming out of that light bulb enough that hopefully we can run some reasonable filters up top. All right, let's take this thing for a little bit of a test drive, and the first thing we've got to do is take a phase measurement, which is, this is the result of that phase measurement that we've got right here. This is an internal calculation to calculate the asymmetry that is a result of the change in speed of light through the beam splitter. By overlaying the spectrum and the phase file that it produces, we can get a really good idea of what the capabilities of this particular source, detector, and beam splitter are capable of. You can see that we have a little like Burj Khalifa right here in the center, and if I move my cursor over to that, that's right at 15,800 wave numbers. That is the wavelength of the helium neon laser. Now, the further to the right that we move into the rest of the visible region, so green, blue, indigo, all of that, ultimately into ultraviolet, and the further to the left we go, we move into near infrared all the way down to far infrared and whatnot. So the green is the spectrum, and we can see the peak energy is way over here. So if I move my cursor over to that's happening at about 9,900 wave numbers. And if I look at my little cheat sheet here, 9,900 wave numbers is very squarely right in the middle of the near infrared. So we can kind of get an idea of where the limitations are. And if we go over to about 8,000 wave numbers, that's where things start to get really bad over here. So we don't want to go below 8,000 wave numbers, which is going to push us further into the near to mid infrared. And conversely, on this side, man, we really don't want to go much further past about 20,000 wave numbers. So 20,000 wave numbers is going to be right on the edge of cyan and blue. So why don't we take a near infrared spectrum of something? So I'll exit out of this screen with a Shift 2, and then we can come over here and do our setup. And within the setup here, we can tell it what phase we're going to use, and then we're going to create a new setup file. And here we go, sigma minimum and sigma maximum. I've got set to 8,500 to 14,000. We just hit return on this. It's gonna run a little bit of math and save that to an internal file that's .steu file, I don't know. It just saves, this doesn't actually talk to the spectrometer on this one. As soon as it gets done, we see that it automatically highlighted reference for us. And what this is going to do is it's going to take a reference spectrum without our sample. This is going to tell us, you know, what the composition of the atmosphere that's around us is, what the composition of that cuvette is, and we're going to use that as a baseline to subtract away from the actual measurement that we take so that we can see what the actual measurement is doing. I'm just going to go ahead and hit enter on this. and it's going to do 10 scans. So the mirror is going to go up and down 10 times at a speed of 0.5 centimeters per second. And then once that's finished, we have a nice reference that we can then view in the display menu here. And there we go, we're ready. So we'll just do a display on here, and we should come up with fref001.ref. So the software here automatically updates the data file in case I want to take a look at it. And yeah, there we go. You can see that we have a nice, whatever that is. We've got some interesting squiggly, wibbly, wobbly, dibbly doos here going on here, but I have no idea what that is. But this is our reference. This is going to be subtracted away from the measurement that we take of our actual sample. And speaking of that sample, I never actually explained the significance of the Everclear in that opening 2-minute ASMR student indie film thing that happened at the beginning. Two things about that right quick though. First, never take a drink of anything out of a cuvette or a test tube. That's just like dangerous and not smart. And I was just trying to get a laugh out of you guys. That's all it was. That cuvette was brand new. It was cleaned with IPA, and then it was cleaned extensively with Everclear, and then it was washed a lot under the sink with regular water. And then the second thing is that when I took the shot, that wasn't actually Everclear. That was just like plain normal water. I don't even drink alcohol. The reason that this is making a debut in this video is because I was looking for things that I can measure in the visible to near infrared range, and it just so happens that on Wikipedia, there is a spectrum of ethanol in the near infrared range. Everclear is pretty much like 95% ethanol. So I figured, hey, let's break the Everclear out, pour it into a cuvette, toss it into the spectrometer and see if the spectrum that we take matches this spectrum here. With our ethanol cuvette in the newly built cuvette holder that we have in there, let's take an actual transmission spectrum here. So we're going to come down to the menu option transmittance here. I'm going to hit return on that. And it's going to tell us a bunch of file names right off the bat here. Below that, we can see that our sigma minimum is 8500, maximum is 14,000, so right in the near infrared range, and 10 scans. So let's go ahead and hit return on that. And here we go. We're doing real deal science in this lab. Like, how cool is this? It's so cool. It's like, it seems really anticlimactic because there's no big noises or anything going on. It just sits there, quietly takes 10 scans, and it's going to give us a real deal result that we can see on the display here as soon as it finishes moving that mirror up and down. And there we go. It finished transferring the data over, says ready right here. So if we do a display, this is our transmittance file. Let's go ahead and hit return on that. So there we go. There's a transmission spectrum of ethanol. Now, the way that a transmission spectrum is read is that at the top here, you have maximum transmission. So that particular wavelength, nothing is stopping it. At the bottom, you have maximum absorption. So at that particular wavelength, nothing is getting through. And so where you see spikes heading downwards is where you're hitting a molecule that is absorbing a particular wavelength of light. So we can see that we have a little spike here. That's going to be right around 11,000 wave numbers. And then we have another little spike over here that looks like it's right around 9,800 wave numbers. And then all the way over here on the far left at 8,400, 8,500 wave numbers at the end, you can see a massive downward spike. Well, what does all this mean? Like, how can we make any sense of this? Well, here's the really tricky thing about spectroscopy, or really any kind of scientific endeavor, and that is that it doesn't actually tell me the answer. All it's telling me is how much energy is being detected by the detector at specific wavelengths. But if you are a chemist and you have a lot of this stuff committed to memory, you can potentially look at a spectrum and say, oh, we're seeing an absorption band at this particular wave number and an absorption band at this particular wave number. That correlates to carbon or hydrogen or whatever. But for me, all I'm trying to do is compare. And so I now have a spectrum of ethanol, and it just so happens that on Wikipedia, as I mentioned earlier, there is a spectrum of ethanol in the near infrared range. Now, it looks a little different than my spectrum because this one is being listed in nanometers and mine is being listed in wave numbers. So actually the scales are flipped. I need to take the right side of mine and move it over to the left side, or vice versa. And actually we can see very similar peaks right here and here. So the spectrum that I took of ethanol matches perfectly to the spectrum that is on Wikipedia. So there you go, confirmed that the ethanol that we already knew was ethanol is ethanol. But this is what science is all about, taking a measurement and comparing it against a known quantity, or comparing it against something that is unknown, like, say, water. How does that ethanol look whenever we fill a cuvette up with water and take another measurement? So just pull the ethanol cuvette out, drop in a cuvette full of water, and let's take another transmittance measurement here. So I'll go ahead and hit Shift 2 to exit out of this screen, and then we're gonna jump back over here to transmittance. All right, now let's rename this to like water R001. So that way it's a similar name to the ethanol 001 file that we had before. But other than that, I'm not gonna change anything. I'm just gonna hit return on this, and we're gonna take a new measurement. It's gonna do 10 more scans of water now. And ready. All right, so let's go ahead and hit enter on that. It's gonna fill in water R001, but I wanna look at both files at the same time. So I'm gonna do an SY0 colon ETHANL001.TRA. I'll go ahead and hit return on that. It did find the file, that's good. So it's gonna load both of those up at the same time here. And there we go. Looks like ethanol is in red and water is in green. And look at that. I mean, we have very similar absorption bands right here at the very edge of the near infrared, but this right through here is wildly different. That is really cool to see. So what's next with this machine? Well, first of all, the light up top is still too bright. I did not put enough diodes in my little diode dropper board. So I think I need to rebuild that board, probably with 8 diodes now. But also I want to start pushing into infrared. But as you can see, we have a pretty hard limitation at 8,500 wave numbers. So where is that limitation coming from? Well, we can look at our little brochure here that lists all the different beam splitters and detectors and all of that stuff. And we can see that our beam splitter is pretty good all the way down to about 4,000 wave numbers. So that's not our limitation. The halogen is also good all the way down to about 4,000 wave numbers. So our limitation is right here on the front. It's this detector. This detector is only good to 8,500 wave numbers, and it's like a hard cutoff there. But I think probably the best option is going to be the DTGS or IMH48. I don't have one of these. I think Mike might have a spare one that I can borrow or steal for a little bit. But I think just that DTGS with this beam splitter and even the halogen lamp up there is going to be an excellent combination that gets us into the near infrared and even flirting a little bit with the mid infrared. Now, if we want to really do infrared right, we're going to need to pull the system down to vacuum. Now, thankfully, I have a vacuum pump. Ugh, oh my God, it's so heavy. I don't know if I can lift this. There it is. Oh, oh man, it's so heavy. Oh, jeez. I have a vacuum pump. It is of unknown condition. It did not come with the Bomem. So we're gonna have to pull that thing completely apart, make sure that everything looks really nice, and we'll learn how a vacuum pump works in the process. And then we gotta come up with different ways to get the correct hoses adapted to the Bomem. Then we'll stuff it behind there, and then we can pull this thing down to vacuum, get into the infrared, and start actually doing some really interesting stuff, because most of the interesting interactions all seem to happen between about 7,000 wave numbers and 1,000 wave numbers. So that's really where we want to be hanging out. But check it out, man. We did real deal science today. We took a proper spectrum of ethanol, a proper spectrum of water. The machine is working flawlessly. I'm having an absolute blast with this thing. So I want to thank you all so much for hanging out with me today, and I hope to see you in the next one.